We have another problem about multiples here. We're trying to find the values of the digit a to make this 4-digit number, 6a34, a multiple of 9. Now, I know how to tell if a number is a multiple of 2 or 4 or 5, but I don't know anything about 9. Well, maybe we can find a rule for 9 like we found for 2, 4, and 5. Now, when I see a new type of problem like this, I like to relate it to problems I already know how to do. And I already know how to handle 2, 4, and 5. And I found the rules for 2, 4, and 5 by figuring out how those numbers were related to powers of 10. So I'll think about the same thing here. How is 9 related to powers of 10? Well, 9 plus 1 is 10. 10 is just 1 more than 9. 100 is 1 more than 99. 1,000 is 1 more than 999. And all those numbers that are just bunches of 9s, they're multiples of 9. That gives me an idea. Let's start off by writing our number, 6a34, in terms of its digits. So it's just 6 times 1,000 plus a times 100 plus 3 times 10 plus 4 times 1. And then we take each of these powers of 10 and we write them as some batch of 9s plus 1. So 1,000 is 999 plus 1. 100 is 99 plus 1. 10, of course, is just 9 plus 1. And 4 is 4. And now we can expand each of these products with the distributive property. So over here we'll have 6 times our 999. And then 6 times 1, that's just 6. Then we have a times 99. A times 1, that's just a. Then we have 3 times 9. And 3 times 1 is just 3. And then we have our lonely little 4 out here. So now look at these strings of 9s. Each one of these is a multiple of 9. I'm going to put all of them together. I'm going to group all of those, because we can rearrange sums in any order we want to. So I'm just going to go ahead and do that. I'm going to put all of these multiples of 9 together. And we know that they're all multiples of 9, because 9 is a multiple of 9, 99 is a multiple of 9, 999 is a multiple of 9. Each of these products is a multiple of 9, so the whole sum of these is a multiple of 9. And what's left over? Well, we have 6, a, 3, and 4. 6, a, 3, and 4. It's just the sum of the digits of our original number. So we've taken the original number and we've broken it up and rearranged it into a big giant multiple of 9 over here plus the sum of the digits of the number. Now, we know this is a multiple of 9. So if this, the sum of the digits, is also a multiple of 9, then we know the original number is a multiple of 9. And because we already know this is a multiple of 9, if this sum is not a multiple of 9, then the original number is not a multiple of 9. So now we just need to figure out what values of a make this sum a multiple of 9. And of course, a is a digit, so it has to be some number from 0 to 9. Well, 6 plus 4 is 10, plus 3 is 13. So this all together is 13 plus a. And now we can see that the only digit that makes this a multiple of 9 is 5. And we've answered our problem. Now, there's something else interesting here. These strings of 9s, they're multiples of 3 as well. And 9 is a multiple of 3, 99 is a multiple of 3, 999 is a multiple of 3, and on and on and on and on. So this number is a multiple of 3, which means that our original number is a multiple of 3 only when the sum of the digits is a multiple of 3. This is a multiple of 3, so if the sum of the digits is also a multiple of 3, our original number is a multiple of 3. So our rule for finding if a number is a multiple of 9 works for 3 as well. So if the sum of the digits is a multiple of 9, then the number is a multiple of 9. If the sum of the digits is a multiple of 3, then the number is a multiple of 3. Now this problem, you know what? This problem reminds me of my birthday party. Doesn't it remind you of my birthday party? No? Well, my birthday's tomorrow, all right? And this reminds me of my party because, well, I'm throwing myself a big, huge party because I'm turning 40. Yeah, that's all. Explain that to your parents. So I'm going to have this big party for my 40th birthday, and I'm inviting 15 million of my closest friends to come to my party. 15 million people, we're going to have a big dinner. Everybody's going to sit down. And I have a bunch of tables, a whole lot of tables, and each table sits exactly 9 people. All right, and I don't want to have extra tables, so I only have enough tables. I get just the right amount of tables. And I was wondering, how many empty seats will I have? You know, if there's only one table that has empty seats, all the rest are full, how many empty seats are at that table? Because then maybe I can invite some more people. So let's see, let's go ahead and tackle that problem. I've got 15 million people at my birthday party. They're seated at tables of 9. One table has empty seats. How many empty seats does that table have? Now, of course, we could just take 15 million, write out 15 million, divide by 9, and look for the remainder, but that's going to take a long time, and I you know me, I'm kind of lazy. I don't want to do that. I don't want to take the long way, plus I'll probably make a mistake while I'm dividing that out. So if I want to know how many empty seats there are, what I'm really wanting to figure out here is how far is 15 million from a multiple of 9? You know, 15 million were a multiple of 9, there'd be no empty seats. How close is it to a multiple of 9? Well, let's look at 15 million. 15 million, wow, that's a long number. Well, we know it's not a multiple of 9 because the sum of its digits is 6. It's just 1 plus 5. So how close is this to a multiple of 9? Well, I know a multiple of 9 is nearby. If the sum of the digits is a multiple of 9, then I get that a number is a multiple of 9. So I can find a very close multiple of 9. The sum of the digits so far is 6. I add on 3 more. The sum of the digits of this number, 15 million and 3, the sum of the digits here is 9. So this number is a multiple of 9. So my 15 million here, they're 3 shy of a multiple of 9. That means that last table that isn't completely full has 3 empty seats. That means I can invite 3 more people. Let's see, who should I invite? How about you? And you? And you?